So thanks for coming to our presentation. We're the student team from the University of Denver working on the Ohio State University.
So just a brief introduction to some, excuse me.
So we're going to start off with some project introduction.
So yeah, just a brief intro to some of the acronyms you may see over the course of this presentation. Obviously, NREL and OSU are ones you're familiar with already, but PV and APV, just how we refer to photovoltaic and agrivoltaic. DER for distributed energy resources and BESS for battery energy storage system are two things to definitely keep in mind though, because they will come into play later. And ANSI, American National Standard Institute, which we as engineering majors are very familiar with.
Yeah, so my name is Achilles Palomino. I'm a student at DU majoring in electrical engineering and I'm team captain, and I worked on the distributed system impact analysis.
Hi, I'm Daniel. I'm the lead solar CAD engineer for our team. I'm also studying electrical engineering, and I worked on the conceptual system design document.
Hi, I'm John Higgins. I'm the lead mechanical engineer, and I worked on the development plan.
Hi, I'm Zishan. I'm working in mechanical engineering.
And I'm Gray Carpenter. I'm a mechanical engineering major and also the financial manager for this project who worked on the financial analysis.
And our main advisor for this is part of the electrical engineering, computer engineering department at DU, and his name is Dr. Goncalo Martins.
So just a brief introduction for the basis to what we're doing. Ohio State seeking carbon neutrality by 2050 as per the Climate Action Plan. And the Climate Action Plan was mainly our inspiration for most of the decisions that went into this. They originally allocated $24 million investment into the solar plan, including all things installation. And so we wanted to stick with that and include that $24 million into the total initial investment of our system, including an integration of electrical vehicles. So either above or below 24 million, no, excuse me, not above, at or below $24 million.
For the conceptual system design, we'll first start off by talking about our design approach. We wanted to develop a rooftop PV system for the medical campus area on OSU's campus, as well as develop an agrivoltaic system for the Waterman Agricultural and Natural Resources Laboratory, as well as install a BESS, or a battery energy storage system, to help with peak load shaving as well as resiliency during outages. So in order to start the design, we first use Google Maps and Aurora Solar to identify areas where solar panels could be placed, such as rooftops without obstruction or major shading, as well as for the agrivoltaics area, land rather than the water inside the agrivoltaics area. As well as after determining which buildings we wanted to have solar panels on, as well as the areas in the agrivoltaics area where we wanted to place solar panels, we needed to use Aurora Solar to determine the optimal configurations for each system. So we simulated using a variety of different settings for panel tilt, fill mode, and panel orientation for each system individually. We then compared the annual production results from each simulation to determine which settings would be most optimal for the highest annual energy production. For the agrivoltaic system, we wanted to make sure that our solar panels were at least 10 feet off the ground. This is to ensure that no livestock is able to interfere with the solar panels, as well as that the solar panels would not be in the way of livestock moving around the area. The solar panels are in a checkerboard pattern to maximize photosynthetically active radiation, or PAR. This is the range of light waves which plants can actually use for photosynthesis to grow and produce energy. So we wanted to ensure that there was enough for the grazing land to actually grow and supply food for the animals. This was based on a Belgian research paper we found where they used this system with potatoes, and it produce great results. We also include a plan to cut down some of the trees on the agrivoltaics area because we did the math, and the solar panels would lead to a larger CO2 emission reduction from generation than the trees would consume or absorb in a year. So for the system design, we'll talk a little bit about the installation sizes and annual productions. These tables show the size and annual production for each building, as well as the agrivoltaics area. The numbers correspond to the map on the next slide. Basically, it'll help you determine which buildings are where, which systems are where, and how big each system is. So this is just a map showing where each system is. So one is the Dodd Rehabilitation Hospital from the last slide. This is basically just to help you guys visualize where the systems are.
Yeah, so on the BASS, we were required to have the James Cancer Hospital, Wexner Medical Center, and the Harding Hospital, but we also modeled some for the Ross Heart Institute and the David Hardin Lung Research Institute. The way we approached that was the first three, we had the peak load that was provided to us. So just added 10% to that to just for safety reasons. And then we input that data into Reopt Lite, which is a tool provided by NREL to get battery size and battery capacity recommendations. And we also did that for the Ross Heart and the David Hart and Lung Research Institute to get those. So from that, we talk a little more in the documents about how many batteries we're going to need, but you would just get the battery size and divide that per individual battery. But we recommend using the LG Chem RESU 10H400V lithium ion battery. So now for the distribution system impact analysis, just talking a little bit, this was seen before already in another NREL presentation, but we want to make sure that we're not going into the upper range, which is potentially what can happen when you start incorporating PV systems. So we kind of want to stay within that green line, ideally. So that's sort of like why we do some DSIA and looking at the heat maps. Just to get a better idea of where we are, I circled the locations that we're focused on. And I do go in further detail in the DSIA document, but when looking at each individual system, we stayed within the rated PV capacity. So there's no violations of that. And that means there's no system overloading. But in the case that we did want to make any recommendations, you could, because we do design it to also like do some grid charging. So in case of any like outages at OSU, you could look into, instead of using the traditional grid following, using some grid forming inverters. And just the incorporation of the BSS itself actually does some of that peak load shifting. So that's already more resilient. Because as the other team mentioned, like at midnight when, I don't know if they said it's peak or not, or like when people get home and they like turn on their TVs for AC, you start to get an instant peak. So these battery systems can actually like help kind of shave that off and increases our total system load capacity. But we don't really need to upgrade anything just because we are within that range. So, yeah.
Next, we have the development plans. The development plan is a document that helps to analyze the feasibility of our designs, as well as take smaller looks into different details around the building area. So that'll look at site conditions such as topography. The topography of the OSU campus does change a little bit from different parts of campus. However, that's not going to affect our build because we're building on top of level roofs. Next, it looks at vegetation. Vegetation on the OSU campus will not affect our build because the trees are not high enough to obstruct the view or the solar collection for the solar panels. In the agrivoltaic section, we do plan to take down some trees, as Daniel mentioned earlier. Next, it looks at adjacent land. Is there any land around our build site that is either going to affect our construction or that our construction could affect? The answer for this in terms of OSU is there's no adjacent land that is going to affect our construction. Next, we look at zoning and permitting. And there are three main permits that we are going to need for our system. That is a building permit, an electrical permit, and a zoning compliance certificate. The next section that the development plan looks at is the construction approach. This helps break down the construction into different phases and certain estimations of how long each phase will take. Lastly, it looks at the feasibility analysis. And this is analysis of are designs feasible? Can you construct them? And can you construct them in a certain amount of time that you said you could construct them in?
So now taking a look at the financial performance. So as I previously stated, we wanted to stick to that $24 million cap for our initial investment. And we were using Energy Toolbase and the initial energy cost, which you see here, we were able to use those inputs to generate a financial performance based on the values afterwards. And if you go to the next slide, you can see the justification for the initial investment as well as the initial cost of everything. So this ended up being a total of about $21.7 million in initial investment, under that $24 million cap we set originally. And with the PPA rate of about 18.83 cents per kilowatt hour, we were able to tabulate a net present value of the customer savings of about $39.8 million over the 20-year span of this entire project. We were hoping for the project to be profitable within 20 years after this investment, and it is definitely set to do that at the current rate, so very pleased with that result.
So now just for some takeaways in the conclusions of this project.
So what we have done so far is to design a reasonable solar PV plus the battery system for Ohio State University. For the future, we need to improve the battery systems, which can provide appropriate and reliable energy supply for each building according to the actual situation. For the panels, we need to find the most reasonable type of placement scheme and keep tracking of their performance to make the appropriate adjustments. Thanks to the project to bring us a lot of gains, including member of the project teams to understand how to build a project, to understand the knowledge that we need to be mastered in the project, and the familiar with some software we need to use. And also to achieve the continuous improvement. We also understand the importance of the project in completing projects. For example, the financial models are a very valuable choice for executing a project choice to get perfect solutions. I think it's a very meaningful thing for things to participate in this project. They not only fulfill the energy needs for the university, but also have a beneficial impact on the surrounding community in many ways. We also hope to participate in some projects like this. Thanks for the watching. Thank you.